Every city on Earth falls silent in the same instant. The sky goes black. Not twilight, not an eclipse. Black. 7 billion lungs gasp against a vacuum where air pressure once held steady at 101 kilopascals. Oceans start to boil, not from heat, but because nothing is pressing down on them anymore. Every flame on the planet extinguishes. Every aircraft drops. And this is only the first second. Could humanity survive just 5 seconds? Because what happens when the atmosphere slams back may be far more devastating than the moment it disappeared. To understand the magnitude of an atmospheric collapse, we must first look at the invisible ocean of gas we live in every day. The air around us is not empty space. It is a heavy, active engine that exerts a constant pressure of about 101 kilopascals at sea level. This pressure acts as an invisible structural support, holding our internal systems in a state of precise physical equilibrium and keeping our bodily fluids safely in their liquid phase. Without this external force pushing back, the delicate balance within the human body would instantly collapse. Chemically, this planetary life support system consists of roughly 78% nitrogen and 21% oxygen, alongside trace gases like argon and carbon dioxide. While nitrogen provides the bulk of the physical pressure that prevents our tissues from expanding, the 21% of oxygen is what fuels human survival, allowing our cells to carry out normal respiration with every breath. Under normal conditions, the human body functions flawlessly, perfectly adapted to the weight of the miles of air pressing down from above. This baseline of 101 kilopascals and 21% oxygen is the absolute foundation of terrestrial life, a highly specialized physical partnership that we rarely notice until it is completely removed. This gas envelope does far more than keep us breathing. It is a highly active shield, constantly interacting with cosmic forces. When sunlight hits the upper air, the gas molecules scatter the shorter, blue wavelengths of light far more efficiently than longer red ones. The intensity of this Rayleigh scattering varies inversely with the fourth power of the wavelength, painting our daytime sky in its familiar blue hue. Higher up, the ozone layer absorbs the sun's lethal ultraviolet radiation, preventing high-energy solar rays from sterilizing the surface. The atmosphere also acts as a global thermal engine, circulating heat to prevent wild, unlivable temperature extremes between day and night. At the same time, this ocean of gas serves as a kinetic defense system, using friction to vaporize the thousands of small meteoroids that plunge toward the surface daily. Even the simplest human experiences rely on this invisible structure. Sound cannot travel through empty space. It requires a physical medium to transmit its pressure waves. The sounds of everyday life, voices, wind, traffic, are only audible because our ears are bathed in a constant sea of air. Each of these systems operates continuously, maintaining a fragile shield that protects the planet from the harsh reality of space. Without this buffer, the Earth is instantly exposed to the raw, unfiltered physics of the cosmos. The instant the atmosphere vanishes, the human body is subjected to a violent physical transition. At sea level, our tissues are built to push back against 101 kilopascals of pressure. When that external force drops to zero, the air trapped inside our cavities immediately fights to escape. For anyone who instinctively holds their breath, this reaction is catastrophic. The air within the lungs expands rapidly, tearing the delicate alveolar walls and forcing air bubbles directly into the bloodstream. Pulmonologist Dr. Alistair Liu, who analyzed historical decompression mishaps, notes that the 1971 Soyuz 11 disaster demonstrates the extreme danger of this acute pulmonary barotrauma, a severe mechanical injury that can cause a collapsed lung or a fatal arterial gas embolism in a fraction of a second. Simultaneously, the sudden pressure imbalance places immense stress on the middle ear. An internal pressure spike of just 17 to 35 kilopascals is enough to rupture the human tympanic membrane. In a total vacuum, the internal pressure blows outward, tearing the eardrums, causing severe pain and immediate disorientation. At the same time, the body reaches the Armstrong limit. At 6.3 kilopascals of pressure, the boiling point of water drops to match the normal human body temperature of 37 degrees Celsius. Because of this, moisture on the surface of the tongue, eyes, and throat begins to vaporize. This ebullition causes rapid swelling and superficial tissue expansion, though the elastic nature of human skin prevents the body from exploding. Blood pressure inside the closed circulatory system keeps internal blood from boiling immediately. Survival in these first few seconds is dictated entirely by oxygen. Unprotected in a near vacuum, the brain has a time of useful consciousness of only 6 to 9 seconds. As oxygen-deprived blood from the lungs reaches the brain, cognitive function collapses. While brain death is not instantaneous, a person has under 10 seconds to act before slipping into unconsciousness, leaving them entirely at the mercy of the silent environment. At 30,000 feet, commercial jetliners and helicopters instantly lose the physical medium that keeps them aloft. Aerodynamic lift relies entirely on atmospheric density. When this density drops to zero, the pressure differential across every wing and rotor blade disappears. Under the classic lift equation, if density is zero, the lift force is zero. This sudden loss of aerodynamic support instantly transforms high-speed aircraft into falling projectiles, dropping into an unrecoverable stall. Control surfaces like ailerons and elevators become entirely useless without a surrounding fluid to deflect. For helicopters, the collapse of air density means rotor blades can no longer push air downward to generate thrust. Fuselages drop immediately. Jet engines, starved of the oxygen needed to burn fuel, suffer immediate flameout and compressor stalls. Their turbines spinning down in the vacuum. Inside these vehicles, pressurized cabins offer a temporary pocket of safety. For a few brief moments, the sealed metal hulls preserve their internal pressure, keeping crews and passengers conscious even as their external environment vanishes. But they are flying through a void. The aircraft are now governed strictly by the physics of freefall, gliding with no air resistance to slow their downward acceleration. On the ground, the loss of the atmosphere halts combustion. Open flames, from simple candles to massive industrial furnaces, extinguish instantly because they are stripped of the oxygen required for chemical oxidation. Only hypergolic rocket propellants or closed, chemically engineered systems carrying their own oxidizer can sustain a reaction. For 5 seconds, the systems that generate power, heat, and flight are completely neutralized, suspended in a silent, drag-free descent. By the second of the atmospheric collapse, the visual and physical reality of the Earth's surface has altered. Looking upward, the familiar blue dome of the daytime sky vanishes. Without gas molecules to redirect the shorter, blue wavelengths of light, Rayleigh scattering ceases. The sky turns into a pitch-black void. The sun remains a blinding white disk, burning alongside stars in broad daylight, devoid of any atmospheric filtering. Simultaneously, a profound silence smothers the Earth. Sound is a mechanical pressure wave that cannot exist without a physical medium. In a vacuum, acoustic impedance drops to zero, making the transmission of waves impossible. Every sound of civilization and nature is instantly muted. The vocal cords of a shouting person find no air to vibrate, and no pressure waves can cross the empty space to a listener. The entire planet falls into an acoustic void. On the ground, exposed water begins a rapid, low-temperature boil. Under normal conditions, atmospheric pressure keeps water molecules packed tightly in liquid form. When pressure drops below the saturation vapor pressure, about 6 kilopascals for typical surface temperatures, water no longer needs high heat to boil. The top layer of every lake, river, and wet surface immediately flash boils into vapor. This boiling is a shallow, surface-limited phenomenon. The rapid vaporization draws latent heat away from the water, cooling the liquid left behind. Because of the immense thermal inertia of large water bodies and the limits of heat transfer, only the topmost microscopic layer undergoes this phase transition. The bulk of the oceans remains intact, insulated beneath a suddenly freezing, boiling crust. Above these waters, a freezing fog rises into the silent black afternoon, carrying away the first gasps of the planet's surface moisture. As the top microscopic layer of moisture vaporizes, evaporative cooling draws latent heat away from exposed surfaces, causing immediate, localized cold burns on unprotected organic material. Yet despite this rapid physical transition, the planet does not instantly freeze or burn. 5 seconds is simply too brief for global, large-scale temperature swings to fully develop across the surface. The immense thermal inertia of the Earth's crust, soils, and oceans keeps the surface temperature temporarily stable, delaying a total thermal collapse. Far above this silent crisis, Earth-observing satellites witness the event from a detached, instrument-based perspective. These spacecraft do not hear the sudden silence of the world below. They register only changes in light and thermal emission. From their orbital vantage points, optical and infrared sensors record a ghostly transformation. The faint glowing ring of the upper atmosphere, the limbs scattering and natural air glow that normally crowns the planet, instantly vanishes. Onboard sensors on platforms like Suomi, NPP, and the GOES network register an abrupt drop in infrared radiance and a complete blackout of the atmospheric edge. From orbit, this space-based observation confirms a global optical and infrared change rather than a local anomaly. The Earth appears as a naked, raw sphere, completely exposed to the cold of the cosmos, waiting for the inevitable, violent return of the air. At the exact 5-second mark, the global vacuum collapses as the planet's gas envelope rushes back toward the surface. This sudden reintroduction is not a gentle settling of air, it is a violent physical collision. The return of the atmosphere creates a massive planetary pressure gradient, driving an inward propagating shockwave directly into the crust. Air masses plunge downward and compress with explosive force as the system seeks to re-establish its baseline of 101 kilopascals. This sudden downpour of air compresses the lower atmosphere at supersonic speeds, creating sharp jumps in pressure, temperature, and density near the surface. This rapid, global repressurization behaves similarly to a massive cavitation bubble collapse, generating extreme wind fields that instantly sweep across the Earth. In a fraction of a second, these winds reach velocities exceeding 68 meters per second, more than 150 miles per hour. This sudden movement of dense air acts like a global blast wave, applying severe structural loading to the built environment. The rapid pressure change creates immense net uplift forces on buildings. Roofs are sheared from their supports, lightweight EPDM membranes peel away, and glass windows shatter inward. Building facades buckle under the physical impact of the pressure front, turning urban centers into zones of immediate structural failure. Industrial warehouses and expansive commercial structures, designed for typical local wind limits, suffer severe envelope failures as wind-induced pressure coefficients are exceeded in milliseconds. For aircraft falling through the sky, the returning atmosphere brings a secondary terminal crisis. Although the return of air density restores the medium needed for aerodynamic lift, the physical transition is too violent to survive. As planes tumble out of control through the temporary vacuum, the sudden wall of returning air strikes them with extreme, asymmetrical dynamic loads. This physical hammering shears wings from fuselages, tears engines from their wing mounts, and destroys control surfaces. Pressurized cabins, already structurally weakened by the 5-second vacuum exposure, are crushed by the sudden, massive overpressure. The return of the air turns a survival scenario into a planetary engineering disaster. The very medium that sustains terrestrial life becomes a kinetic weapon, transforming the return of pressure into a physical hammer that levels power lines, collapses structures, and destroys almost every flying vessel before flight crews can attempt recovery. Survival during the 5-second vacuum itself is highly possible. Human skin and blood vessels are elastic enough to prevent the body from rupturing, and the brain can endure up to 9 seconds of oxygen deprivation before losing consciousness. An individual in a sealed room, or even someone outdoors who did not hold their breath, would likely survive those 5 initial seconds. The true danger arrives with the returning air. The resulting pressure shockwave and subsequent structural collapses constitute the primary threat to human life. Survival outcomes depend entirely on location, altitude, and immediate surroundings. While someone in an open rural area might experience eardrum rupture and temporary hypoxia, those in urban centers must survive falling concrete, shattering glass, and collapsing roofs as buildings buckle under the sudden aerodynamic loading. Beyond direct trauma, computer models of planetary shockwaves project a rapid, cascading collapse of societal infrastructure. High-voltage power transmission lines fail under the wind stress, triggering blackouts that cut electricity to municipal water systems and essential medical facilities. Transport networks fracture as debris blocks roads and derailed trains halt supply lines. In agricultural regions, models suggest that severe wind shear and soil erosion could stunt crop production for several seasons. This widespread physical damage leaves global supply chains broken and rescue networks entirely overwhelmed. In the hours following the event, survivors confront a severely damaged planet where basic resources are scarce, and the path to systemic recovery remains dangerously uncertain. We live at the bottom of an invisible ocean, entirely dependent on its crushing, life-giving weight. This thin blue line is all that shields us from the lifeless void, As we continue to alter our skies today, we are reminded of how easily fragile systems can shatter. Our survival is leased, not owned. If this scenario gripped you, consider subscribing for more.